Hello friends, and welcome to some stoichiometry, topic S1.4 Counting Particles by Mass. This is an introduction to the mole. Our guiding question: how do we quantify matter on the atomic scale? Here are our understandings. Should you want to pause the video and read them, there they are. And our objectives for today: we're going to define the mole. We're going to do some conversions, so have your calculators nearby. We're going to also define lots of phrases that are super similar but have some important differences. We're going to look at relative atomic mass and relative formula mass, and then also molar mass. We're going to wrap up with some more conversions, more calculator time. You might also want your data booklets. In chemistry, we spend a lot of time with balanced chemical equations like this one. Unfortunately, these coefficients do not tell us something super convenient like grams that we could measure on our scale. Instead, they tell us how many molecules we have reacting. If I want to make 2 molecules of ammonia, NH3 is ammonia, then I'm going to need to react 3 molecules of hydrogen gas, and there's an invisible one molecule of nitrogen gas here. Of course, that's not going to be enough for our scales to perceive, and so we've got to scale these guys up. So perhaps instead of 1 molecule of nitrogen gas, I could have 12 molecules of nitrogen gas and 3 dozen hydrogens and 2 dozen ammonias, except that's still not going to be enough for our scales to perceive, so we've got to scale up bigger. There are 12 things per dozen. We're going to use this other counting number, Avogadro's number, the mole number, 6.02 times 10 to the 23rd things per mole. What that means is I could have 1 mole of nitrogen gas, that's 6.02 times 10 to the 23rd molecules of nitrogen, reacting with 3 moles of hydrogen gas, that's 3 times 6.02 times 10 to the 23rd molecules of hydrogen gas. That's going to make 2 moles, or 2 times 6.02 times 10 to the 23rd molecules of ammonia. This is enough for our scales to perceive. Avogadro's constant, also known as the mole number, we represent it with capital N, lowercase a. It's given to us in section 2 of the data booklets, but you are going to use this number so frequently, my friends, you're going to have it memorized whether you want to or not. And again, our unit label is per mole. What per mole? Just about anything that we want to count. We usually talk about elementary entities, which are just things that we count. It can be atoms, it can be molecules, it can be ions, it could be electrons, things in chemistry that we want to count. So let's do a few conversions with the mole number. Again, this is given to us in section 2 of the data booklet. How many neon atoms in 2 moles of neon? So we're going to start with this one, our given, and we're going to flip it into our atoms, what we want to find. We always start with a given, 2 moles of neon, and we're going to use what we like to call railroad tracks, and I don't know why we call them that because I don't think they actually look like railroad tracks. What they really are fraction bars stuck to each other. And what's super cool about fraction bars is that we can cancel out tops and bottoms. You know that 2 over 2 in a fraction, those 2's cancel out and you are left with 1. This is what we want to do. So we're going to take this mole and I'm going to put it on the bottom, so that my moles and my moles end up canceling out, just like my 2 and my 2 canceled out. And I want to flip my moles into atoms, and so I'm going to put atoms on the top of the fraction bar. I need to make this whole entire piece right here. This piece needs to be equal to 1 because I don't want to change the value of that 2. I just want to make it look different. And so what we're going to do is figure out how many atoms are equal to 1 mole. Well, we know that there are 6.02 times 10 to the 23rd anythings, atoms included, in 1 mole because section 2 of the data booklet tells us so. What can we do now? Oh, friends, we can cancel out moles on the top and moles on the bottom because, again, we just have these 2 fraction bars stuck together. So now all I have to do with my handy-dandy calculator is multiply 2 times 6.02 times 10 to the 23rd. And then we're going to divide, because fraction, we divide the denominator. We're going to divide by 1, which we don't actually have to do because that doesn't change the value of the numbers. What do we get? We're going to get 1.204 times 10 to the 24th. What's my unit label? Well, moles is gone. All I have left are atoms. And this is not our final answer because we have to do a sig fig check. So I've got 1, 2 sig figs here and 1, 2, 3 sig figs here. This is actually an infinite number of sig figs because it's exactly 1 mole. I didn't round to about a mole. Definition-wise is exactly a mole. And so we are going to round to just 2 sig figs because we're going to keep the smaller of the numbers. So final answer, 1.2 times 10 to the 24th atoms of neon is equal to 2 moles of neon. Let's do another one. How many hydrogen atoms in 0.10 moles of, this is ethanol, C2H5OH. Again, we're going to start with our wanted. We're going to flip into our given. 0.10 moles of C2H5OH. Fraction bars, railroad tracks. So the first thing that I need to do is get to hydrogen. I don't want ethanol. I need to get rid of ethanol and flip it into hydrogen. I want to get rid of ethanol, and right now it's on the top. I'm going to put it on the bottom so that it goes away. I want to flip my ethanol into hydrogens. How many hydrogens in 1 ethanol? Well, we've got 5 plus 1 makes 6. 6 hydrogens in 1 ethanol, so I can cancel out my ethanols. I now have hydrogens, but I have moles of hydrogen. I don't want moles of hydrogen. I want atoms of hydrogen. So we're going to have to extend the fraction bar just a little bit longer. I have moles here. I want it to go away. I'm going to put it on the bottom. I'm going to turn my moles into atoms once again because I want atoms of hydrogen. How many atoms in a mole? Well, Avogadro's number tells us there are 6.02 times 10 to the 23rd in 1 mole. So now I can cancel out that mole number and I can get my handy dandy calculator, and we're going to go 0.10 times 6 times 6.02 times 10 to the 23rd divided by 1 divided by 1. And that gives me 3.612 E22 according to my calculator. What does that even mean? Well, E22 simply means times 10 to the 22 power. So we can get rid of that times 10 to the 22. We also need to do a little sig fig check. I've got 1, 2. I've got 1, 2, 3. These ones, again, I didn't round to about 6 hydrogens per ethanol molecule. It is exactly 6 hydrogens per exactly one ethanol molecule. So these guys actually have infinite numbers of sig figs. They don't count. So I'm going to keep 2 because 2 is fewer than 3. 1, 2. So my final answer is going to be 3.6 times 10 to the 22 hydrogen atoms in that 1/10 of a mole of ethanol. Let's do one more. How many electrons in 1 mole of hydrogen gas? So let's start with our 1 mole of hydrogen gas. Remember that hydrogen gas is diatomic, friends. Brinkelhoff, H2 is hydrogen gas. Railroad tracks, fraction bars. We need to convert to electrons. Oh my goodness, how many electrons in hydrogen? Well, so 1 hydrogen has 1 electron, but if it's hydrogen gas, they're sharing that pair of electrons. So how many electrons? Looks like 2 electrons in every 1 hydrogen gas molecule. So now I've gotten rid of our H2s. I have moles of electrons. I don't want moles of electrons. I just want the number of electrons. So we're going to get rid of that mole number. Once again, put it on the bottom. We're going to put electrons on the top. How many electrons in 1 mole of electrons? Well, there are 6.02 times 10 to the 23rd electrons in 1 mole, because that's however many things there are in a mole of anything. And so now we are going to go 1 times 2 times 6.02 times 10 to the 23rd divided by 1 is going to give us 1.204 times 10 to the 24th electrons. Sig fig check. We're going to keep 1, 2, because these guys, again, infinite numbers of sig figs. 1, 2, 3 here. Keep 1, 2, and our final answer is 1.2 times 10 to the 24th electrons. Our lovely periodic tables give us lots of information about all of these atoms and elements that we're talking about. So if we're looking at nitrogen, nitrogen has 7 protons because the atomic number tells us so. And then this 14.01 is the weighted average of isotopes of the element. We learned how to calculate relative atomic mass a while ago. We talked about how we convert our percent abundance to a decimal, multiply by the mass of each isotope, and then add. Here, what we're going to think about is why there's no unit label on relative atomic mass. So when we figure out the masses of the different isotopes, remember that isotopes are atoms of the same element, same protons, different numbers of neutrons, and therefore different masses. To figure out the masses of these isotopes, we use a super cool thing called a mass spectrometer. That mass spectrometer is going to give us masses of these isotopes relative to 1/12, the mass of one atom of carbon-12. And so we're going to give that a unit of 1, and it could be 1 AMU, atomic mass unit, and then the atomic mass units that we have up here, and because it's relative, those cancel out. So relative atomic mass, A sub R, relative atomic mass is unitless. So the relative atomic mass of nitrogen is 14.01, no units. And neon is 20.18, no units. Carbon dioxide, we're going to add up all of the different atomic masses to find the formula mass of CO2. And it's going to be 12.01 plus 2 times 16.00. And we add that up, and it looks like we get 44.01, no units. AlF3, aluminum fluoride, we're going to go 26.98 plus 3 of those fluorines, 19.00, hidden behind my scribbles, is going to give us a grand total of 83.98. No units. No units on our relative atomic masses, our relative formula masses. But almost the same thing is the molar mass. Molar mass is the mass of 1 mole of a substance. So notice there's no more relative here. It's just the molar mass. And so, my friends, we finally have a unit. The unit is going to be in grams per mole, grams per mole. So CO2 we just calculated was 44.01. The relative formula mass is going to be 44.01. The molar mass is 44.01 grams per mole. And then aluminum fluoride, its relative formula mass was 83.98. No units. Molar mass, now it's grams per mole. Good. Tiny, tiny small differences, but important differences. Relative, no units. Molar, units. Grams per mole. Let's go back to our calculators, some more conversion practice. We did this problem a couple slides ago. We started with our 2 moles of neon. We got rid of moles by putting it on the bottom. We turned our moles into atoms by putting it on the top. And we know that 6.02 times 10 to the 23rd atoms in 1 mole is going to allow us to cancel out the moles. And then when we multiply 2 times 6.02 times 10 to the 23rd, and then we divide by 1, we're going to get, with a sig fig check, 1.2 times 10 to the 24th atoms of neon. But what if I switch up this problem just a little bit, and now I have 2 grams of neon instead of 2 moles of neon? We're still going to start with that given, 2 grams of neon. How many atoms in a gram? We have no idea. Our periodic table doesn't tell us that. We don't have a piece of the data booklet that tells us how many atoms in a gram of neon. But what we do have is our periodic table that tells us that 1 mole of neon is equal to 20.18 grams. So we're going to get rid of our grams, put grams on the bottom with our 20.18, and we know that this 20.18 grams of neon is equal to 1 mole of neon, because this is the molar mass in grams per mole. Grams per mole. So now we can cancel out, whoa, I almost canceled out neon, cancel out grams top and bottom. You know what I have now? Moles of neon, which is basically just this problem. We're going to tack on 1 more piece of our fraction bar. I've got moles on top. I want it to go away. We're going to put it on the bottom. We're going to turn our moles into atoms, put atoms on the top. We're going to add in Avogadro's number, 6.02 times 10 to the 23rd atoms in 1 mole. So now our math, we're going to multiply the tops. 2.0 times 1 times 6.02 times 10 to the 23rd. Divided by 20.18 divided by 1. Calculator time, we're going to go 2.0 times 1 times 6.02 times 10 to the 23rd power. We're going to divide that by 20.18. Divided by 1 is going to give us 5.966, so many decimal places, times 10. Whoa, 10 to the 22 atoms of neon. Let's do our sig fig check. I've got 2, I've got 4, I've got 3. We're going to keep 2. 5.9, but that 6 is going to round that 9 up. We're going to get 6.0 times 10 to the 22 atoms of neon in 2 grams of neon. 2 more practice problems, and we are going to call this lecture done. How many formula units in 242 grams of sodium nitrate? Step 1, we need to turn sodium nitrate into a formula that we can use. Sodium is Na and nitrate is NO3. It's one of our polyatomic ions. Remember that nitrate has a charge of -1 and sodium has a charge of +1, so luckily the charges balance out already. We don't have to scale either of these pieces. So we're going to start with sodium nitrate in our given, and we've got 242 grams of it. We are looking for formula units, which is kind of the same thing as a molecule, except because this is an ionic compound, we can't really call it molecules. That's only for molecular compounds. Instead, we have formula units. How many NAs and NO3s do we have? So step 1 is going to be to convert our grams to moles, because our periodic table gives us molar mass. Grams on the bottom and moles on the top. We're going to add sodium and nitrogen and 3 of these oxygens. 22.99 plus 14.01 plus 3 times 16.00 gives us a grand total of 85.00. We're going to keep our sig figs, grams per 1 mole of sodium nitrate. Step 2, we're going to get rid of our moles now that we've gotten rid of our grams. So we're going to do that by putting moles on the bottom, and we're going to convert our moles to formula units. How many formula units in 1 mole? Well, there are 6.02 times 10 to the 23rd anythings in a mole, and so we're going to cancel out moles top and bottom. Let's do some calculating with our handy dandy calculators. We're going to do 242 times 1 times 6.02 times 10 to the 23rd divided by 85 divided by 1. That's going to give us a grand total of 1.7139, lots of decimal places, times 10 to the 24th. Sig fig check. I've got 1, 2, 3 sig figs. I've got 1, 2, 3, 4 sig figs, and 3 again. We're going to keep 3. 1, 2, 3. That 3 is not going to round up that 1, and so our final answer is going to be 1.71 times 10 to the 24th formula units of sodium nitrate. Last practice problem, 8.1 times 10 to the 24th molecules of dinitrogen tetroxide is equal to what mass? Let's turn our words into a formula. Dinitrogen tetroxide, nitrogen, we've got 2 of them. Oxygen, we've got 4 of them. So I have 8.1 times 10 to the 24th molecules of N2O4. We're going to convert that into moles first, because I do know from Avogadro's number how many molecules in a mole. We're going to put molecules on the bottom. That says molecules. We're going to put mole on the top. I know that there are 6.02 times 10 to the 23rd molecules in a mole. So here we have joyfully canceled out molecules top and bottom. I now have moles of dinitrogen tetroxide, but I want to turn it into mass. That's grams. So I'm going to take those moles, put moles on the bottom, put grams on the top. Let's do some more addition. I need 2 nitrogens and 4 oxygens. So handy dandy calculator time. 2 times 14.01 plus 4 times 16.00 is going to give us a molar mass of 92.02 grams per mole. So my friends, we now can cancel out moles top and bottom. With our calculator, we're going to multiply top and divide by the bottom. Sometimes I actually like to go not all the tops and all the bottoms. So what I'm going to do with my calculator now is 8.1 times 10 to the 24th power. And then I'm going to divide by that 6.02 times 10 to the 23rd power. And then I'm going to multiply by 92.02, because we know that multiplication and division I think the mathematical property is commutative. We can do it in any order. So now my final answer is 1,238.142, lots of decimal places. Let's do a sig fig check. I've got 2, I've got 3, I've got 4. I get to keep 2, so we're going to keep 1, 2. Be careful. We're not going to turn it into 12. That doesn't make any sense. It is 1,200 grams of dinitrogen tetroxide. And on that note, we have begun to quantify matter on the atomic scale. We talked about mole, Avogadro's number. There are 6.02 times 10 to the 23rd things in a mole. We converted between moles and molecules, relative atomic mass and relative formula mass. We're using the mass numbers on the periodic table, but these guys have no units because it's relative to 1/12 of carbon-12's mass. Molar mass, however, does come with units. It's grams per mole. How many grams in 1 mole? But it's pretty much the same thing as relative atomic mass and relative formula mass, just with the unit. And then we did all of those practice conversions. Great work today, my friends.